Hi guys, welcome back to Algebra. Today we are starting a new chapter, chapter 3. And so in this video, we're going to talk about the graphs of polynomial functions and also identifying and classifying polynomial functions. So we will be taking notes on page 118 in your workbook, but we need some preliminary information about polynomials and how to classify them before we start taking notes. So I will scroll down and show you. Yes, I am going to be doing stuff from page 118, but grab a sheet of paper and maybe glue this in your workbook, maybe even on page, 116, because you do need this information. You may have seen it before, but let's talk about what a polynomial is. A polynomial is a string of terms that are written and are separated by either a plus or a minus. So each term is separated by a plus or a minus. So right here, I can see there are 1, 2, 3, 4 terms in this polynomial. So one thing to note about polynomials is that the terms are separated by positives or negative signs. The other thing to note is that the terms that have x's, the exponents on the x's are positive. So the variables have positive exponents. And most of the time, you'll see polynomials written in standard form. Standard form is where you write the polynomial so that the exponents are going in descending order on the variable. So for this polynomial p of x, if I put it in standard form, it looks like it already is, where you have x to the third, then x squared, and then x to the first. So standard form, 2x cubed minus 5x squared minus 2x plus 1, or plus 5. So the variable exponents go in descending order, where the terms are written so that variable exponents are in descending order. So now let's talk about the degree of a polynomial, because you can name a polynomial based on its degree, because polynomial is a general term for a certain type of function, and then you can break polynomials down into smaller terms. So we name polynomials both by degree and also by the number of terms that they have. So I'm going to pause the video and write down some examples, and then I'll come back and talk about each one. So here we have some example equations, and you can name a polynomial based on the degree. So what is the degree? The degree is the highest exponent on the variable when you're looking for the degree of a polynomial. So if I look at, let's start at the bottom, and actually let's start about 2. It'll make more sense that way. So if we start at 2, when I look for this one, the degree of 2, that means that when I write my equation, the highest exponent on the variable is 2. So when that happens, we have a quadratic function or a quadratic polynomial. And if you notice, the last chapter we studied, the whole chapter was about quadratics or parabolas, and all of our equations had an x squared. And we also know that the graphs of quadratic functions are parabolas that either open up or they open down. If the degree is 3, that means that the highest exponent in the polynomial is a 3. Even though there's a 2 later, but the highest exponent's a 3. We call that type of polynomial a cubic polynomial. And those cubic polynomials either look like this or like that. And we'll talk about how you can tell the difference in just a little bit. Let's see, if the degree is 4, that means the highest variable exponent is a 4. We would call that quartic. If the degree is 5, the highest exponent on the x would be a 5, and we would call that quintic. Oh, I can't spell. Erase. Q-U, quintic. And then if the degree is 6 or higher, so the highest exponent is 6 or higher, we call that whatever degree. So you'll call it like the nth degree. Meaning whatever the degree is, you'll just say that like th. So this is a degree 6, so I would call this 6th degree polynomial. And we'll come back and talk about the graphs in just a little bit. If the degree is 0, that means that there is no x, or if there were an x, let me draw like an invisible x here. The degree on the x would be 0, and anything to the 0 power is 1. So 3 times 1 is still 3. So that's why we call it the degree is 0. We would call this a constant function because it's constantly 3. It's never going to change. But if it's not constant, then you could put any value for x in and the y value would change. Constant means the y is always going to be 3 no matter what the x is. If the degree is 1, that means the exponent, even though you don't see 1, it's understood to be 1. The exponent is 1, so we call that linear. And so you know that lines either look like this or like that, based on their slope. And then constants are horizontal lines. So that's one way you can name a polynomial, based on the degree. You'll also name a polynomial based on the number of terms it has. So let me pause the video, add some examples, and we'll come. Looking at these examples, I count the number of terms. So I'm going to start with 2 again. So 2 terms meaning anytime you see a plus or minus, that's how you know to start counting the next term. So I have 1, 2 terms. So when you have 2 terms, we call that a binomial. Bi meaning 2. 3 terms, 1, 2, 3, we call a trinomial. Tri meaning 3. If it has 1 term, we call that a monomial. And if it has 4, 5, 6 or more, so really 4 or more terms, so this one has 1, 2, 3, 4, 5 terms, we just get tired of naming them and we just call it a polynomial. A polynomial. And poly means many. So monomials 1, binomials 2, trinomials 3, polynomial is 3 or 4. Now when you name polynomials, you need to name them by both, let me see if I can zoom out a little bit more, by both the degree and the number of terms. So you need to give both names. It's kind of like a first name and a last name. So let me come over here to an example. Let's say I had y equals 3x squared minus 7x plus 4. So I would give this a name based on its degree and also based on the number of terms. So I see the degree is 2. So that means if the degree is 2, I would call this quadratic. The number of terms, there's 1, 2, 3 terms, which makes it a trinomial. So I would classify this polynomial as being a quadratic trinomial. So now we can turn to page 118 in your workbooks and look at these examples here. So example 1a, it's saying what is each polynomial in standard form? What are the leading coefficient degree? And what's the number of terms? And I also am going to say, because we can and because I know you guys are so smart, we're going to classify. the polynomial. So that means name it according to degree and number of terms. So I need to put it in standard form. That means I need the term with the highest exponent first. So I'll put that negative 3x to the fourth first. The next highest exponent is cubed, so minus 5x cubed. Then plus 2x plus 6. So this is standard form. It said, what's the polynomial in standard form? Check. Then it's going to ask me to find the leading coefficient. The leading coefficient is the coefficient of the term with the highest variable exponent. So my highest, so I'm going to come over here and say that my leading coefficient is going to be the number with the highest exponent, and the coefficient of that, negative 3. Then it tells me to identify the degree. So my degree is, the highest exponent is 4, so the degree for this one is 4. Then it wants me to count the number of terms. How many terms here are there? Let's count 1, 2, 3, 4. So 4 terms. Oh, I don't need to write terms again. There's 4 terms. And then I'm told to classify. So let me grab this. I need to classify. So remember, we classify based on the degree and based on the number of terms. So I'm going to go back up to my chart, look for the degree 4 and the number of terms. So when I go back up to my chart, degree is 4, so it's quartic, and the number of terms, 4 more, polynomial. So we're going to say this is a quartic polynomial. Now you may be asking yourself, why are leading coefficient, why did they ask me to do this? Well, because remember earlier when I said we're going to come back to these graph examples? That's where it's really important. Zoom out here. So you said graph examples, and I said I was going to tell you how to tell what's happening with your graphs. Well, let's just say if you have a quartic equation, the ends of it, now polynomials, when you start graphing them, they get kind of crazy in the middle, but we can definitely tell you what's going to happen on the ends. So quartic equations definitely point up on both ends, on the left and the right, but in the middle they might like go up and down and up. They might just look like a parabola, but there's something else that happens. We need to do further analysis to figure that out. So they're either both ends are going to point up or both ends are going to point down. So you'll see me like say, so this or that or that. When a polynomial is quintic, the left side will point down and the right side will point up. That's what's going to happen. Or the left side's going to point up and then the right side's going to point down. Now we can summarize all of that into a chart that's going to help us determine what happens with the end behavior, or what's happening on the end of a function. So you need to also add this end behavior. End behavior is saying what's happening, here's the coordinate plane, what's happening on each end of the x-axis. Is my graph pointing up on the right and up on the left, up and down? So it all depends on the leading coefficient and the degree. So we're going to make a chart. And we'll say leading coefficient up here, I ICIENT. Okay, so the leading coefficient could either be positive or it could be negative. And then on the right side will be our degree. And the degree could either be odd or an even number. Okay. If the degree is odd and the leading coefficient is positive, the left side of your function will point down, the right side will point up. We're not sure what's happening in the middle, but we do know for sure that's what's going to happen. If the leading coefficient is negative and the degree is odd, then the left side will point down, or sorry, the left side will point up and the right side will point down, and then in the middle, we don't know yet. If the degree is even, leading coefficient's positive, both ends will point up. If the leading coefficient is even and the leading coefficient is negative, degree is even, leading coefficient is negative, both ends will point down. So let's take our good old friend y equals x squared. The leading coefficient here was 1, so it was positive, and the degree was even. So positive, even degree, put it right here, and yes, we already know that y equals x squared is that nice parabola. So it does match up. Okay, so keeping this in mind, let's look at example 2. Use the leading coefficient and degree of the polynomial function to determine the end behavior of the graph of each function. So first I want to make sure that my function is in standard form, x to the 6th, x to the 5th, 4, 3. Yeah, it's in standard form. So I need to know my leading coefficient. It's positive 2. So leading coefficient is positive. And my degree is 6. So the degree is 6, which is even. So if the leading coefficient is positive and the degree is even, let's go back up to our table. Positive, degree is even. We've got an instance where both ends point up. So that tells me I don't know what the graph of this polynomial looks like, but I do know that on the ends, without having to grab a calculator, both ends are going to point up. Now, this is great for drawing pictures and describing the end behavior with pictures, but it's hard to communicate this in writing and also like typing it out on a piece of paper. So you need to know how to write this with correct notation. So if I want to say the end behavior, I can do it like this. As the x values approach negative infinity, which is talking about, that's the left side. Let me highlight that. So on the left side. As the x values approach negative infinity, my y values are approaching, so I look at my y values, they're going up, 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 up. So the graph is going up, so the y values approach positive infinity. That's the left side. For the right side, as the x values approach positive infinity, so this is the right side. Talking about this right here. The y values also go up, up, up. So the y values approach positive infinity. Now you'll see end behavior written like this and like this. So know that you'll be responsible for both notations. Let's see. This one, let's go ahead and look at this one as well. Leading coefficient for part B is negative 5. And the degree is odd because the degree would be 3. So I have a negative leading coefficient and an odd degree. So let me go back up to my chart, grab a highlighter, see where I am. Leading coefficient is, I have an odd degree and I forgot what the leading coefficient was. Negative, odd and negative. Okay, so odd and negative puts me right here. ends will look like this. So let's describe the left side. As the x values approach negative infinity on the x-axis, the y values of the graph would approach positive infinity. So as the graph goes to the left, the graph also goes up. And then the right side, as the x values would approach positive infinity, the y values would approach negative infinity. Then if you flip the page, we're going to skip because you don't need to look at every single thing from the section. Look at page 120 and you'll see a graphic here. Notice this is the graph of f of x, and f of x has a positive leading coefficient and an even degree. So here's what the graph looks like. Ooh, that's fun. And so we're just asked to identify some key features. So let's go through this. Number of terms, 1, 2, 3, 4, 5 terms. Degree, highest exponent is 4. Leading coefficient, we've done that a couple times. In this case, it's that coefficient right there, 1. In behavior, both ends are pointing up. So for the left side, as the x approaches negative infinity, the y values approach infinity. So I say left by saying the x values, talking about these x values, they get more and more negative. Then for the right side, as the x values, so on the x-axis, as the x values get larger and larger and larger, or approach positive infinity, the y values are going to continue to go up. So the y values also approach infinity. Turning point. So this is new. A turning point is anytime a graph changes from decreasing to increasing or increasing to decreasing. So right here, it's kind of hard to figure out what they are because you can't really see, but you could graph this on Desmos and then click on each point to find the turning point. So for right now, you just need to label them as turning points because you can think of it as the graph turning around. So it was decreasing, changes to increasing. X-intercepts are the same. So this graph has x-intercepts at -4, -2, 1, and 3. So -4, 0, -2, 0, 1, 0, 3, 0. Here's a new term, relative minimum. A relative minimum happens when the graph changes from decreasing to increasing. So my graph is decreasing, changes to increasing. So right there, that's a relative minimum. Then it's increasing, but then it's decreasing, changes to another one. Relative meaning like it is a minimum, but it may not be the absolute lowest minimum. So you just need to be able to know where they are. Again, if you could graph it on Desmos, or if you graphed it on Desmos, you could find those exact points. But when you identify the relative minimum, know that you just identify the y value. Relative maximum is like the kind of opposite of that. So my relative maximum is when my graph would change from increasing to decreasing. So right there, that would be a relative maximum. And again, for relative maximum, you're only going to give me the y value. So if you see problems like this on your assignment, you would graph this in Desmos, find those points, and enter those values.